Okay guys, so welcome to IR. This is the very first lab of Organic Chemistry 1. So I'm going to go over a little bit of the IR theory with you guys so you kind of know what to expect when you start running your samples. All right? So we're going to begin talking about IR theory by looking at the electromagnetic spectrum, which I'm sure you guys are all familiar with from general chemistry, other courses you've taken, maybe in physics. But the electromagnetic spectrum is just the way that we measure light or radiation, right? So there's a certain wavelength of light that we can see, from red to violet all the way through, and then at one end of the spectrum, higher energy light, we have ultraviolet, and then eventually we have X-rays, gamma rays, and things down there. And at the other end, if we redshift the light, go lower energy, we have IR, or the infrared spectrum. And then if we keep going down this way, we get microwave and a bunch of other things. But right here, this area, IR radiation, that's what we're going to be using to identify some of our organic molecules. So what happens when IR light hits our sample is some of it just passes right through the sample doesn't react at all, and that's what we call transmitted light, right? Just transmitted directly through the sample. But some of the light, depending on the energy level of the light, when it hits the sample, it's going to make the sample vibrate and start moving around. And so instead of that light being transmitted, that light is going to be converted into mechanical energy as the molecule starts to shift, the bonds kind of stretch in different ways, or they bend in different ways, things like that. Okay? And what's going to determine what wavelengths of light are going to excite your sample and get it vibrating or stretching in certain ways are the functional groups that are present in that sample. So a functional group is just a common chemical motif, right? It's something like a repeated pattern, a certain arrangement of atoms that we see in a bunch of different molecules. And they all have a bunch of fancy different names, and you're going to start learning those as you go through organic chemistry and get more familiar with them. But let's look at one example really quick, okay? Let's look at an alcohol or an OH group. So this is a very common chemical motif. Okay, so an alcohol OH group, and we also are going to have an alkane on this molecule. For an example, we're going to use ethanol down here. So in addition to alcohol, it has an alkane, which is just a single bond between carbon atoms. So the alkane on this molecule is going to be this section down here, and the alcohol, OH, is right there. Okay? So when we put a sample like this, like ethanol, onto our IR spec, we're going to have a bunch of different wavelengths of radiation, of IR radiation hitting it. Okay? So as it scans through all these different wavelengths, eventually it's going to get to 2850 to 3001 over centimeters. All right? And so when that wavelength comes through and it hits the molecule, it's going to see this alkane group, and this alkane group is going to be like, oh yeah, that wavelength's like my jam, So it's going to start vibrating in a certain way. And so that light is not going to be transmitted, it's going to be absorbed by the molecule. Then we keep going through, and there's some other light that the molecule doesn't really care about, so it just passes through. We have some transmitted light. And then we get over to 3200 to 3600, 1 over centimeters, wavelength of light, okay? And so then when that hits the molecule, it goes to this alcohol, and the alcohol's like, oh my gosh, I love this wavelength of light. And so now your alcohol group's gonna start vibrating in a certain way. And so then that light's going to be absorbed, all right? And then the way we see this on an IR spectrum is on a graph just like this. So on the x-axis, we have wave number. The wave number is just the measurement of the energy or the wavelength of light that we're hitting the sample with. And then on the y-axis, we have percent transmittance. So all the way from 0, 50, all the way up to 100% transmittance. So if you have a point on here, a certain wavelength where you're at 100% transmittance, that just means your IR radiation isn't interacting at all with your molecule. Okay? It's just passing right through, molecule doesn't care. But when it starts to dip down and your percent transmittance gets really low, that means that all of this light is now being absorbed. And certain functional groups, as we know, like certain amounts of light. So if we go back to our example, we see that the alcohol group absorbs light in the 32 to 3600 range. So here, we have this peak at about 3500. And that makes sense, because that lines up with our alcohol group right here. We keep going along, and we see here, we have another peak. This peak between 2850 and about 3000, if we go all the way down, boom, there it is, about 3000. And so we know this peak probably lines up with our alkane group right here. Okay? So different molecules with different functional groups are going to have different spaces where they absorb light on the IR spectrum. Usually, when you're looking to identify a molecule, you're going to go from 1500 all the way up. Below 1500, that's what we call the fingerprint region. Fingerprint. This region is really, really detailed. Usually, you'll see a lot of noise, a lot of spikes, and things like that. But generally, as humans and not computers, it's sort of hard to identify molecules based on what's going on in the fingerprint region. Computers can do it really, really well because it's super detailed, but our eyes aren't really trained to get into the nitty-gritty. There are a few exceptions to this, but generally, once you hit 1500, you don't need to worry about marking those peaks and trying to figure out what they correspond to on your molecule. Okay guys, so now I'm going to show you how to run an actual IR sample. So this is the IR machine. We've got these beautiful tiny instruments here. And so if you look really closely, you'll see there's a big silver circle under the arm. And inside of that big silver circle, we have a little tiny clear circle. The little tiny clear circle is actually the diamond, and that's what's going to be holding the sample. So we want to make sure that we're centering our sample on that little diamond there and make sure it's completely covered. Okay, so go to the computer. You're going to open up Microlab, which is like this little red circle here. And you're going to push start. And it's going to instruct you how to run a sample step by step. So the first step is to clean the crystal. So take a little chem wipe, and you're going to get one of these little bottles of ethanol, kind of push down on the top. And you're going to clean off the crystal really, really well. Make sure that diamond's all clean, it's not discolored, there's no solid. And clean off the arm, just like that. And then we're going to go to next. And it's going to start collecting our background. Perfect, okay. So it has a background measurement taken. So if there's any gunk that's left on our crystal, it's going to subtract that out of our final sample. All right, so now, using our gloved hand, we're going to open up our liquid sample, pull up a little bit, and just put on enough to cover the diamond, just like that, okay? We're going to go to next. And it's going to start running the sample like in real time, but it's not saving that data. So we're going to go to next again. And then it's going to start actually taking our sample measurement. And we're going to end up something that looks like this. Okay? So if you right-click, you're going to go to Pick Peaks. And then it's going to tell you to select peaks for labeling. So you're going to draw a blue line over all the peaks of interest, and it's going to tell you exactly what the wave number those peaks correspond to is. So let's see, I'll get that one there. Maybe I'll take these little ones, grab a couple of these. Maybe we'll even go all the way down here towards the fingerprint region and get some of these peaks too. All right? So I've labeled probably more peaks than I need to in this case, but better to have too many than too few. The next thing you're going to do is go down here to the snipping tool, which is like this white oval with the blue scissors. And this is just going to take a little screenshot. So you go to New, and it's going to go like that. And then you're going to make sure you get this entire white rectangle here. And now we have our sample. We're going to go to File, Save As, dun, dun, dun. And then we're going to name our sample. We're going to call this my initials MW1, save it as a JPEG to the desktop, and then either email that to yourself or put it onto a flash drive. Okay? So we're going to close this down, and then we're going to push Done on the Microlab, and then we're going to clean off the crystal again. So another chem wipe, a little ethanol, wipe it down really, really well. Just like that. Okay, cool. And then it's ready for the next user to go. All right, and then finally, if I were going to run a solid sample and not a liquid sample, you would put the solid sample again on the crystal and then turn the arm until you hear it click just like that. Okay? Otherwise, run the sample exactly the same, pick the peaks exactly the same. Also notice when I was running the IR sample, I was using my gloved hand to handle all the chemicals and my ungloved hand to touch the computer. Never put gloved hands on the computer.